the session. Okay, let me start a new drawing. Okay, so right, the next topic which I would like to discuss is the quantum repeaters. Okay, are and the repeaters going to create the opportunity, and they're going to provide the opportunity for us called entanglement swapping. Okay, that is what we want to discuss. So I have a PPT for you as well, right? So, but like more than that, I want to have, okay, I want to have, okay, so I want to explain, yeah, this one, right? Yeah. So, so first thing first, the question is, what is this quantum repeaters are? Okay. So what is this quantum repeaters are? In classical communication, if you see, right, so we use amplification like anything. Okay, why? Because the signal which I sent from place 1 to place 2, okay, it's not going to sustain for a longer distance, because there is a chance of being affected by the environment. Okay, that's why, see, when I'm speaking, I use a loudspeaker and there is amplification setup, amplifier is there. Okay, so even if I'm talking louder, there may be chance my voice strength is not sufficient to reach at some point. So I have to enhance my voice and then communicate to a longer distance. So I need amplification there. Okay, and sometimes there is some students are like in the front are disturbing my voice communication. People at the end may not be able to hear if I don't have an amplifier or if I don't have a sound system there. Okay, so that is why we use in a classical communication amplifiers. So basically the repeaters which we are addressing in today's session is a kind of an amplifier effect. Remember, such in the case of classical communication, you are may be allowed to amplify the signal by cloning the signal multiple times, but in the case of quantum repeaters, it is not possible, and the people don't use such like repeating like such a amplifying effect. Okay, so that's what the second statement says. So in the quantum repeaters, the extension of information from point 1 to point 2 or for a longer distance is done by called like done by using a process called entanglement swapping. It's like entanglement is swapped. Okay, we swap gadgets between two siblings. Okay, right? So sometimes the siblings don't like whatever they got. They swap between each other the gadgets whatever their parents bought. So that is what we were trying to do. Some swapping of entanglement. So in the end, what happens is it allows one to create a signal transition or signal transfer between a very longer distance than the usual scenario what we had in the first case. So let's see what is that quantum repeating and quantum swapping is all about. Okay, right? So let's say there are two parties like A and B, and another party C is there. Okay, right? B and C. Okay, so let's say B is neighbor to A and C. Okay, if A and B has shared an entangled pair of atoms between them, and also B is somebody who shares entangle between C also. Okay, so B is a common between two parties A and C. Now what B can do, he can do some kind of mumbo jumbo with him so that the A and C gets connected up. Okay, it's a B is like somebody who connects the A and C. So B is a very crucial thing whatever happens at the B, you can say that is a B is acting like a repeater, and B at B, the process is taking place in such a way the entanglement exists between A and C and B and C, sorry, A and B and B and C gets swapped in such a way A and C gets entangled. Okay, that's a very interesting thing. We'll see that. In fact, it's not just a fancy thing, it is possible. Okay, so in each case, A, B, C, we are talking, this is actually called a quantum memories. So, right, each node get entangled with its neighboring node here, right? Okay, so entangling, swapping happens. See, A and B is entangled, C and B and C is entangled. So their individual entangles swap in such a way A and C gets entangled. Okay, so that is what the entanglement swapping here. In this way, what I can do, I can keep extending the entanglement for a longer distance in such a way I'll have very long communication possibility. So let me use my hand note at this point so that I can explain better. Okay. Okay. So what I'll have, let's say there is a party A. When I say party A, it could be a quantum node, a kind of a qubit, and there is a party B. Okay. There is a party C. Okay. So this guy gets entangled, and this guy also has an entanglement between B and C. Okay, and this guy can do something here in such a way entanglement is created between A and C. Okay, so that is what this is a entangle. This plays a repeater and it does swapping, entanglement swapping. The same thing can also be understood in another way. What is that is, let's say there is a party A, there is a party B, there is a party C, there is a party D. So these two are entangled and these two are entangled. Now you see, remember, B and C has nothing in common. Okay. Okay. So case 1, case 2. Okay. So here we can do something between B and C. So that I'm sorry, A and D gets entangled. Okay. And now question is, what happened to B and C? B and C got vanished. They may become a classical anyway. So B and C initially were quantum in nature. The moment I do some kind of a swapping process, entanglement swapping process, in that case, B and C loses their quantumness and becomes classical. There are no more quantum nodes for me. So I only worry about what is the nature of information existence between A and D. So here A and D are entangled. Okay. Now see, earlier A and B is entangled, C and D are entangled. Now A and D got entangled. So the distance is now doubled between A and D. Okay. Why? So you can ask a question. Why not create entanglement between A and D straight away? Why we are doing this mumbo jumbo in between? The answer is very simple. Let's say I am not able to create entanglement between very longer distances. Let's say there is a node here, A, and node D is much far. I can't create a paired entangled atoms or a pentagonal photons send to A and D at a time. Let's say D is so far. When I send a photon, entangled photon, that can't travel to the D, because on the way it might interact with the environment and interact with some noise around, and it may die down, it may lose its quantumness, it may lose its information. So that's why what I do, I just find myself how long my photon can travel without being affected. So I realized that up to B it can travel, so I'll send to B. And at just in the vicinity of B, I'll have one more C. Okay, what I mean is I'll have equally spaced nodes this time. Okay, so between A and B, I create entanglement. B and C, I create entanglement. C and D, I create entanglement. So I have entanglement here, equally spaced entanglement. Okay, I does quantum repeating effect. Okay, first when I do quantum repeating effect, I create, see here in this case, first A to B, B to C, C to D. Now when I do when I do repetition or swapping, A and C get entangled. Now again I create a swapping at this point. So then A and D gets entangled. Okay, so the information now can be easily communicated between A and D the moment entanglement exists. Okay, so this is some kind of a explanation, the like schematic explanation how entanglement swapping is going to facilitate us the information transfer between 2 points. The moment there is an information storage possibility is there, what happens? You have a chance, okay, you have a chance to communicate between two parties which are having entangled share. So so the moment you have two entangled shared atoms, you can do teleportation between them, you can do quantum communication between them, you can do quantum key distribution between them. So the moment these entangled pairs are existing between two parties, you can do lots and lots of applications. That's why having entanglement is very, very crucial. Okay, so let me go to the slides and see what the slides are actually telling me about. Okay, so we just discussed this. Okay, so let's go to the methodology. So methodology, how this is possible. First, let's say I have an entanglement between two parties, any two parties. Let's say I can have entangle bell pair between two parties. Let's say I'm talking in terms of photons being entangled between two parties, which are like horizontal, horizontal, and vertical, vertical kind of a polarization. Okay, so bell pair is given at the bottom. You see 0, 0 and 1, 1. How are we creating such an entanglement? In a quantum circuit fashion, it's very simple. So you have a quantum resistor. So bell pair creation. I will just recollect bell pair creation. We have one quantum resistor starting in 0, another quantum resistor starting in 0. Let's say I have Hadamard gate on the first register and I send through. I use a C0 gate, and C0 gate would act from the register 1 to register 2. In this case, right? So what I'll have, okay, at this point I'll have a superposition after the Hadamard gate. Okay, here I still have 0. With the C0 gate, what happens? I'll have entangle created between two resistors. Okay, right? Correlation between existing between A and B. Remember, I cannot say individually that there is some state exists at the bottom register, individually some state exists at the top register. I can't say. Together, I have to say the entanglement exists between them. So let's say now the top atom is A, bottom atom is B. So initially I can write them as a tensor product which represents them as separable states. They're brought together, but they're still separable. The moment entanglement is created, which has to be written as a compound system, we cannot separate them quantum mechanically. Remember, quantum mechanically they are not separable, but spatially they can get separated. Means I can put them carefully to individual boxes, send them apart, they can still exist in this quantum nest or quantum entangled state if I am careful enough. Okay, so that is what entanglement bell creation is. Now, so let's say I have that between two parties. Okay, let me go to the next slide. Okay, let me use, okay, slideshow. So there is a lot of information is there in this particular slide. Please don't worry, we'll go one by one. Okay, so just see on the very extreme left top, we have a Hadamard gate followed by CNOT gate, creating a bell pair between quantum resistor 0 and 1. Both were starting in 0, 0 state. That's all. So very simple, left hand side. Similarly, let's say I take two more quantum resistors, okay, 2 and 3. I use the same kind of a bell pair creation, or you can say EPR states are created using the same Hadamard gate, same kind of Hadamard gate and the CNOT gate. Now, if you see here, there is an entanglement exists between quantum resistor 0 and 1 and quantum resistor 2 and 1 individually between their pairs. Okay. Now, I was intended to have initially the entanglement between the quantum resistor 0 and 3, but the problem is, let's say my C0 gate cannot extend from quantum gate 0 to quantum gate 3. It is not possible to extend. Means the information of 0 cannot be traveled through the C0 gate to the 3 because I have an inability in communicating to that level. Let's say in that scenario. So I have to create entanglement between 0 and 3. What I will do, whatever entanglement gates which I used earlier, I'll use in a reverse fashion. This time C0 gate first and Hadamard gate later. The moment you do this, okay, it is like something called the Bell state measurement. What is this Bell state measurement is? Okay, so let me quickly explain what is the Bell state measurement. Okay, so then only you will understand what is this Bell state measurement is. Okay, so that's very crucial. If you understand that, becomes easy, straightforward. Okay, so let's quickly understand what is measurement in the first place. Okay, so we have a Z gate, we have a X gate. Okay, Z gate means Z matrix and X matrix. If you want, I can specifically write down this is 1 0 minus 0 minus 1. X gate is 0 1 1 0. As you know, Z gate acts on 0 gives the same state. Z gate acts on 1 just gives a negative parity state of 1, which implies Z has plus or minus quantum eigenvalues and 0 ket and 1 ket as eigenstates. Okay, very important. Similarly, x acts on 0 gives you 1, x acts on 1 gives you 0, which means 0 and 1 cannot be eigenvectors of x. Okay, so let's say I want to have eigenvectors of x. Let's find out x acting on plus ket state. What do you know? Plus ket is 0 plus 1 divided by square root of 2, and minus ket is 0 minus 1 square divided by square root of 2. Now x acting on 0, use this relation. You see, x acting on 0 gives you plus as it is. But x acting on minus ket gives you minus of minus ket, which means x has eigenvalues plus or minus 1, eigenvectors plus ket and minus ket. Okay, right? So what you see here is there is a basis for that, which is 0 ket and 1 ket with base eigenvalues plus and minus 1. X has again plus ket minus ket as a base and corresponding eigenvalues are same. Okay, right? Now, what is this? Why did I bring this? Because I can create a measurement tools or some kind of a projections using this basis elements. What is that? Is I can create a measurement tool for the x basis using 0 as 0 outer 0 mx, sorry, this is not x, this is z, okay, 1. I can create a measurement tool like this. Similarly, I can create a measurement tool for x plus ket is plus outer plus minus outer minus. What is the use of these things is, okay, remember, let's say I have a quantum state like this, alpha 0 plus beta 1. Now, what is the value? Okay, if I am writing it on a paper, this is what you are seeing. Let's say I am given a qubit as it is, like a material is given. To find what is alpha, what is beta, what you have to do? You have to add a m z0 cat measurement tool on psi, which is going to give you, okay, 0 0 acting on alpha 0 plus beta 1. Okay, to find the exact alpha value, you have to take a expectation value of this, means on the left hand side you have to multiply with the bray of psi. So there I'll have psi on the left also, 0 alpha star plus 1 beta star. Okay, so this is going to see inner product between 0 and 0 is 1. Okay, inner product between 0 to 0 is 1. What is left? Alpha 0 plus alpha star into alpha I'll get. So I'll get alpha absolute square. So I'll get what is the chance of quantum state psi to exist in 0 is given by alpha square when I try to find the measurement operator z on c on the given quantum state. Similarly, measurement operator 1 gives you beta square. If the quantum state is prepared like alpha plus ket state, beta minus ket state, in that case, the measurement operator x plus would give you alpha square and measurement operator m minus would give you beta square. Okay, so this is going to give you this. Fine. So these are like measurement operators are very, very important. There is a m plus and m plus m minus corresponding to x basis, m0 and m1 corresponding to z basis. Okay. So what I mean is, if I have a basis elements like a 0 ket and 1 ket, you are going to create a projection operators like by taking outer product. So what is the beauty of this projection operators are? They are going to tell me whether the given system is existing in this state or this state. Okay. Now come back to the Bell states. What are the Bell states I have? There is a Bell state beta 0 0, which is 0 0 plus 1 1 divided by square root of 2. Okay. There is a Bell state beta 0 1, which is 0 1 plus 1 0 divided by square root of 2. Okay. There is a Bell state 1 0, which is, let's say, 0 1 minus 1 0 divided by square root of 2. There is a Bell state beta 1 1, which is 0 0 minus 1 1 divided by square root of 2. So these are all Bell pairs. Okay. If you find whether these four are orthogonal or not, absolutely, they are perpendicular to each other. Okay, they are perpendicular to each other. They are actually, sorry, they're actually normal to each other. Okay, so they're perpendicular to each other, normal to each other. That means I can call them orthogonal, and they form a basis of bell states. Okay, so you can just create bell basis using them. Okay, that means the moment I have a bell basis, I can use them to create a measurement operators which are going to look like beta 00 outer with itself, beta 1 beta beta 01 with itself outer product, I mean beta 10 outer, okay, beta 11 outer with beta 11. Okay, so what these basis elements are going to tell me, when I take them, let's say measurement operator is created, m beta 00 is created, and you act on a given quantum state, let's say compound quantum system E and B, okay, and it is going to tell me whether A and B is entangled or not. If A and B are entangled in a fashion of beta 00, which is 00 plus 1 divided by square root of 2, I will get this as some non-zero. If it is 0, this has 0 value output, which means the psi AB is not entangled in this fashion. Okay, okay, that is the beauty of this bell pair, right? So now coming back to this setup, whatever we have here, if you see, okay, just wait a minute, let's go back to the previous slide. Yeah, okay, so quantum state 0 and 1 is entangled, 2 and 3 is entangled. If you just check a bell pair measurement, okay, between 0 and 1, of course they're entangled. 2 and 3, of course they're entangled. Okay, so instead of just doing a bell pair measurement, okay, finding entanglement is there or not, you do the reverse bell pair measurement. If you just do between 0 quantum state 1 and 2, it's very interesting. We know that there is no entanglement between them, but I am doing a bell pair measurement using that operator which we constructed. If you do that, interestingly, what it is going to lead is, it is going to lead entanglement between 0 and quantum state 0 and 3. Okay, so now in the form of measurement, I have given you the mathematics, but literally using quantum gates, what it is you just take a Hadamard gate after the C0 gate. First you take the C0 gate followed by the Hadamard gate. If you do that, that is what the bell pair measurement is. Bell measurement is. The moment you do that bell measurement, and you can just do the classical measurement from quantum to classical. Here, this measurement tool is there for both quantum resistor 1 and 2. If you do that, you are going to get some classical output 0 and 1 in the top and bottom. If the classical output 0 and 1 is there, so on the top register, if you have the quantum resistor 1 leading to 0, in that case you don't do any Z operation in the first register. If you get 1, which means you do the Z operation on the top. It's like control Z between quantum resistor 1 and 0. Similarly, quantum resistor 2 and 3, I'll have a C0 gate which is going to act only when second register going to 1. Okay, this is what the bell measurement is all about in a quantum circuitry. In a quantum circuitry, bell measurement of whatever I was showing here, the measurement operator is converted into the quantum gate operations here. The moment you do it, interestingly, something would happen between quantum resistor 1 and 3. Initially, they were not entangled. This time, they become entangled. Very, very interesting, right? So the entanglement is extended between quantum resistor 0 to quantum resistor 3. Okay, right? If A is a ground station and D is a LEO satellite, what would be B and C be? Some relays. Okay, there is a good question asked by Hemani Koshalji. Okay, so he's asking, let's say we will have quantum resistor 0 in the ground, quantum resistor 3 in the satellite. What would be the nodes of quantum resistor 1 and 2 should be placed? Okay, so you can have some kind of a drones. Okay, so drones at different heights between the satellite to the ground station. So these drones are some satellites below the top satellite you can have, and you can extend the extend the entanglement between all the way ground to satellite in a free space communication. As of now in India, this is being pursued at Raman Research Institute and also CDAC Pune. People are working. As of now, what they are going to do, they are going to use the multiple drones to create an entanglement swapping and extend the entanglement in a free space. Okay, with optical fiber, it is not that a bigger thing, even though it has its own challenges. But the ultimate goal for people is to extend the entanglement to a very large distance, like somebody was asking, like Mr. Hemaniji is asking, extend to entanglement between ground station to the satellite. So between these two nodes, we need to have in this like between nodes could be a drones. Okay, and on the drones we can have quantum nodes latched. Okay, so now let's go to the next slide. Okay, so let's say I want to extend this to much longer distance. What I mean is, let's say I have 8 registers. Okay, so I want to, they're separated for a longer distance. So for sure I can create entanglement between any two coupled pairs which are in the vicinity. 0 and 1 entangled, 2 and 3 entangled, 4 and 5 entangled, 6 and 7 entangled. Now the bell measurement is done between 1 and 2 and 3 and 4. Sorry, not 1 and 2 I'll entangle, and I will have bell measurement between 5 and 6. What happens here? Entanglement is across, like shared across 0 and 3 and 4 and 7. Now again what I do the entanglement between 3 and 4, right? Bell measurement between 3 and 4. Immediately what happens? Entanglement is shared across 1 and 7, sorry, 0 and 7. See, in this way you can keep going and extend the entanglement for a very longer distance. So on the right extreme you see a density operator as a density matrix shown with this what is this kind of a checkerboard. Wherever there is a gray color which correspond to amplitude, amplitude of half, sorry, it's a probability of half. Wherever there is no amplitude, it is 0. So that is what the density matrix would look like. Okay, oh fine. So that's the entanglement swapping protocol for 4 pairs. Now you can understand the mathematics, how it is ensured. How it is ensured? The moment I do the measurement, bell measurement, the entanglement gets extended. It's not just a simple statement saying I just do the swapping and create the entanglement between two extremes. It's not that. Okay, there is a mathematical explanation. Let's say you divide the entire circuitry into layer by layer. So there is a very initial state, let's say T0 time. There is the information, all the resistors were put in zeros. Okay, after T0, let's say at time T1, if you see, there are two hadamarts are being acted on, first register and the third register. So there is a superposition is created for first register and the third register. Okay, now that's what you see at a T1. You see there is a superposition is created for first register and the second register, the zeroth register and the second register. Okay, then if you write literally what is the state would look like at T1, you see the first register, the zeroth register is in superposition state plus, second one is just 0, third one is plus, and the fourth one is 0. If you write that in a column matrix, here I am written as a row with a transpose. Okay, so that is what psi of T1 would look like. Okay, now let's go to the next level, that is a T2 level. So at T2, what was happening? Before T2, there was a C0 between quantum resistor 0 and 1 and quantum resistor 2 and 1. You know how the C0 gate works, right? So with the C0 gate action, you can just implement it, and if you see what would the result would look like, result would be simply entanglement state between, or a bell pair between 0 and 1 resistor and 2 and 3 resistor. That is straightforward. Both were put in a tensor product, which means two entangled pairs were put together. Nothing else is yet acting between these two entangled pairs, but they just brought two into the vicinity. Now I will have first C0 gate after T2 gate, so T2 level after time T2. If you see, C0 is there between 1 and 2 registers. So that's what I have written. Nothing acting on quantum resistor 0 and nothing acting on quantum resistor 3, but there is a C0 acting between quantum resistor 1 and 2. So that's what I have written. Then if that such a quantum resistor gate acts on psi of T2, what I will be getting, if you carefully see the mathematics and try to act a C0 gate, and you would end up with the psi of T3, whatever is given in the bottom. Okay, so now let's go for T4. At T4, psi of T4, what I will have, I actually acted a Hadamard gate only on quantum resistor 1, nothing else on quantum resistor 0, 2, and 3. So let's do that. Quantum resistor Hadamard gate only on the second resistor, and everywhere else is identity gate. So you see, identity gate is on even 2 and 3. That's why it is written in a tensor product. So if you add, you will have some quantum state of psi of T4, which is written at the here at this level. Okay. Now at psi of T4, okay. Now what I'll do, I'll make a measurement. I'll make something called horizontal polarization measurement. Means I'm trying to find whether the system is in 0 state or 1 state. Okay, so that was the measurement operator, which was like a measurement operators which I defined earlier for a Z gate. Remember, for a Z gate, I did the 0 and 1 basis measurement. Similar to that, I just represent them in the form of polarization, in the form of photon qubit measurement. So if I do that, let's say I get 0 and 0 as an output. So what I mean is quantum resistor state 1 and quantum resistor state drops down to 0 and 0 state. If they're dropping down to 0 and 0, let's say they're falling into horizontal and horizontal polarization, means I can just simply ignore not doing anything between 0 and 1, 0 and 3, because actually entanglement is already established between 0 and 3, even doing nothing. See, earlier, if you see here, okay, if you see here, okay, the first sketch for entanglement swapping, I have a controlled Z gate between 1 and 3 after the C0 gate and Hadamard gate. So the bell measurement is a combination of all the C0 plus Hadamard and then measurement followed by control Z and control C0, right? So that is the entire bell measurement is all about. But when it comes to here, in this case, there is no need to do anything because both resistor 1 and 2 have comes out to be 0 and 0, which means the quantum resistor 0 and 3 already got entangled. That is what's shown here in your psi of T5. Okay, psi of T5, you see the entanglement is existing between quantum resistor 0 and 5. Okay, so the entanglement swapping is occurred between 1, 0 and 1 pair and 2 and 3 pair, and I ended up with quantum entanglement extension. Okay, fine. So when it comes to actual experimental registration, experimental realization, what it would look like is something like this. I have two lasers, I have a half wave plate, and I have a quarter wave plate, followed by some barium borate crystal, which would produce something type 1 down conversion. Means with a single 100 joule photon, I'll have two photons coming out with 50 joules. It is called spontaneous photonic down conversion. Let's say 100 joule is converted to two photons of 50 joules. That is what happens at both the places, at the top and bottom. Basically, I am going to create entangled pair at the top and entangled pair at the bottom. Okay, so when entangled pairs are produced like this, okay, what I will do now, I'll have taken the one entangled atom from the top, one entangled atom from the bottom, and put them and make them interact with a beam splitter. You see BS, that is the beam splitter. Actually, it is actually doing something called a Bell measurement, or it's a part of Bell measurement, followed by on the top I have half wave plate, and followed by horizontal polarization checking or horizontal polarization filter, and then I let that everything goes through the optical fiber into avalanche photodetectors. Okay, now the way I explained earlier, it's like we are taking things for granted that entanglement is created, entanglement is extended for a very longer distance. It is not that straightforward. In fact, there is something called time tagger, or it's actually counted. So between some billions and billions of photons coming out in each sequence, only there is entanglement exists between certain set of pairs. Okay, you have to pick those pairs and then count them. That is what the setup is going to do. But nevertheless, whatever entanglement comes out, which is going to be very, very handy, so that could be used to do some cryptographic encryption, and that could be used for some communication, serious secure communication. Like people can do that. So that is what the experimental setup would look like. Okay, so there are some highlights. Okay, so simplified protocol, it's a very simplified classical disamplification channels are involved here. Okay, less sensitive to synchronization, right? Okay, so which can be modular and scalable with optical communication. So promising for fiber based and satellite quantum internet. So recently, like not recently, a year back, so Professor Prem Kumar from US Maryland University, they have showed entanglement distribution across the telecommunication optical fiber. So that's a very promising thing. There is a signal, classical signal is there. In the same classical signal carrying fiber, they distributed this kind of entanglement. Okay, so in summary, the new entanglement stopping protocol simplifies the design because we can't have the cloning, so we need to look for some alternative, that is a repeater. So that does the entanglement swapping. So experimental results confirms the correctness and high fidelity here, means we can actually succeed. So it reduces the cost and complexity of quantum repeater networks. Okay, too many repeats is not required, and strong candidate for deployment in future quantum internet. Okay, so that is the summary of this entanglement swapping. Okay, right? So in summary for all the three sessions, so we started with what is the quantum memory. We built that idea of quantum memory on the classical memory knowledge. Okay, so we built that on a classical memory knowledge. Okay, fine. So what are the requirements for a classical quantum memory to have a perfect memory properties. We saw that, and there are various platforms where quantum memory could be realized. One is atomic ensembles, that is using electromagnetic induced transparency or Raman Stokes or anti-Stokes. They use property called slowing down the light through this EIT, electromagnetic induced materials. In a way, slowing the light is treated as some kind of a memory. And radiant ion doped crystals also gives this effect. It's called atomic frequency comb based memory. And atoms and ions can anyway exist in superposition state. In that way, they can have the memory effect. And in the solid state case, NV centers in diamond are inside the carbon. We can have a dipole which is sensitive to the external field. So we can induce some kind of a memory inside which can be retained for some time and retrieved later. Okay, photonic memories, as usual, photons carries the polarization information and they will be a very good photon memories. Okay, transmons, artificial atoms. So these are simple LCR circuits which are going to show some of the capacitor charge states as a quantum states. In that way, we can realize memories. Okay, so individually we discussed each one of them. So I will be uploading this slides. Okay, and also I'll be uploading my handwritten text, so you can go through it and understand better. Or if you want somebody missed, they can re-watch the video and they can understand. If you still not understood, you can always come back and reach to me by my email or by phone, and I would be very very happy to explain and ensure that you get the idea. Okay, so once again, thank you very much for listening to me. I hope I have not bored much. So yeah, I take this opportunity to again thank Dr. Rajendra for giving me the opportunity to explain all these quantum features to you. So also I thank EIT Academy for a continuous support for me in lecture all the knowledge what I have to the all the participants. So thank you very much. So I'll hand over to the Academy now. So Academy can take over.
Thank you very much, sir, for this wonderful talk. So I hope you have answered all the questions, sir.
Yeah, ma'am. I think I was keeping an eye on the chat box if there is any questions. So wherever there is a question, I was in between. I was trying to answer. Let me see if there is anything I missed. Yeah, everybody was. Yeah, I was able to answer the questions till 3, 4 o'clock. Let me see.
So, sir,
Yeah.
there is a common question. Your contact number is needed.
Yeah, you can share, ma'am. I consent to share my phone
Okay.
number and contact number, whoever wants it.
Okay.
Okay. So you can call me, or it's better if I respond like 95% time. If I'm not responding, I'm in a meeting or somewhere. So in that case, you can send me WhatsApp message. I'll definitely get back to you people.
Yes.
Huh?
Thank you, sir. We now close this session. Thank you, all the participants. Bye bye.